Hey there. Today we are diving into some key linear algebra topics that, let's be honest, can feel a little abstract, but I promise you, they are secretly your best friends when it comes to exams. We're going to cover vector spaces and orthogonality, but really our main mission is to unlock some amazing shortcuts that'll help you crush those problems.
So, if you are getting ready for a big test, you have come to the right place. We're about to take these textbook definitions and turn them into actual, practical tools you can use to nail even the trickiest questions. Let's get into it.
All right, first things first, vector spaces. The best way to think about a vector space is like the sandbox or the playing field, where all of linear algebra happens. And before we can start playing and building cool stuff, we've got to know the rules of that sandbox.
Okay, so the formal definition, it can look a little intense. It's basically a set of vectors where you can do two things: add them together and multiply them by scalars. And for it to count, it has to follow 10 specific rules or axioms. But here's the thing, you almost never have to memorize all 10 of them.
Really, we can boil all those rules down to just three big ideas. For a set to be a vector space, first, it's got to have the zero vector. And second, this is the most important part, it has to be closed. That's just a fancy way of saying if you take any two vectors from inside the space and add them, the result has to land inside that same space. And same thing for scalars. You scale a vector and it can't just suddenly jump outside the lines.
Now here is where this becomes super useful on an exam. You're probably not going to be asked to prove all 10 axioms. What's way more common is a question like this. Is this smaller set of vectors, which lives inside a bigger vector space, also a vector space on its own? We call that a subspace, and testing for it, well, there's an amazing shortcut.
This right here is your go-to for exams, the 3-point subspace test. To prove something is a subspace, you just check these three things. Number 1, does it have the zero vector? Check. Number 2, is it closed under addition? Check. And number 3, is it closed under scalar multiplication? Check. If you get a yes for all three, boom, you've proved it's a subspace. It's so much faster.
Okay, let's switch gears. A lot of the time, we're handed a basis, the fundamental building blocks of a space. It's kind of messy. The vectors are pointing in all sorts of weird directions, and it makes calculations a pain. But what if we could tidy that up? What if we could build a new, clean basis that makes life easier? That is exactly what the Gram-Schmidt process does.
So, why even bother with this? Well, with a standard, messy basis, trying to do things like projections can be a total headache. But with an orthogonal basis, where every single vector is at a perfect 90-degree angle to every other vector, those same calculations become incredibly easy. It's the ultimate work smarter, not harder move in linear algebra.
So how does this whole thing work? Gram-Schmidt is just a step-by-step recipe for building this nice, clean basis. You start by just picking one vector from your old, messy set. That's your first clean one. Then you grab the next vector, and you basically figure out the part of it that's already pointing in the same direction as your first one, and you subtract it. What you're left with is perfectly perpendicular. You just keep doing that for all the vectors, always carving away the parts that aren't orthogonal.
Okay, we've laid all the groundwork. Now it is time for the part you've been waiting for, the exam power-ups. I've got 3 game-changing shortcuts that build on everything we've just talked about. These will give you a serious advantage when that exam clock is ticking down.
That's right, 3 essential tricks you absolutely need to know. Let's jump into the first one. Power-up number 1 is a total lifesaver. Normally, proving that a set of vectors is linearly independent means you have to set up this whole system of equations and show the only solution is 0. It's a lot of work. But here's the shortcut. If you can show that the set of vectors is orthogonal, you're done. An orthogonal set of non-zero vectors is always linearly independent. No extra calculation needed. Seriously.
Power-up number 2 is for a super common situation. What happens when a system of equations, ax equals b, just has no solution? We call that an inconsistent system. You can't find an x that makes the equation perfect, but you can find the next best thing. You can find the x that gets you the closest possible answer. And how do you find that best approximation? With this incredibly powerful tool called the normal equation. Instead of trying to solve ax equals b, which you can't, you solve this new equation. A transpose times a times x equals a transpose times b. The amazing thing is that this new system always has a solution, and that solution gives you the best possible fit. This is definitely one you'll want to commit to memory. And our third and final power-up is all about finding a vector's coordinates. With a normal, messy basis, you're back to solving a whole system of equations again. But if your basis is orthonormal, which just means it's orthogonal and all the vectors have a length of 1, the whole thing becomes ridiculously easy. This is where the magic happens. To find the coordinate of your vector w along any of the basis vectors, you just calculate the dot product between them. That's it. No system of equations, no complicated algebra. Just a handful of simple dot products. It is by far the fastest way to find coordinates, but only if that basis is orthonormal.
So there you have it. We've gone over the rules of the vector space sandbox, the power of building clean orthogonal bases with Gram-Schmidt, and 3 massive shortcuts for your exam. From the 3-point subspace check to the normal equation and those super easy dot product coordinates, you are now armed and ready to tackle these problems with way more confidence. Good luck on that next problem set.